Okay, we've been talking about parallelograms for the last, what, 3 or 4 lessons, something like that. Today we're going to switch gears just a little bit, and we're going to talk about a thing that you might have heard of before, but you probably haven't studied a whole lot. Trapezoids. Okay? Trapezoids, and they talk about a thing called a kite. Kites. And that's actually a geometric figure, okay? A kite. You know what a kite is, right? You fly it up in the... But this is not like some crazy looking kite. It's just a regular old plain kite. That's a crazy Z. What if I go like that? It's kind of like a cursive Z. What? You don't like that Z? What's wrong with my Z?
It looks like a 3. I'm like looking at them like that.
Oh, you guys don't write cursive, do you? So it's a Z. Can't believe you guys don't write cursive. I don't know. Mine's kind of like a hybrid between printing and cursive, I think, sometimes. Yeah. Oh, man. Even when I'm writing emails or IMing or whatever you do on there, or even texting, I always capitalize, I punctuate, I do all that stuff. I don't know. It was just drilled in me, when I was a kid, to make sure you spell it right and punctuate, punctuate, is that right? Punctuate? Okay, and all that kind of stuff. All right, anyway, let's talk about a trapezoid. I probably should have drawn one before, but that's okay. Let me just talk about what a trapezoid is. Remember the definition of a parallelogram was? It was a quadrilateral with both pairs of opposite sides what? No, not congruent. That wasn't the definition. The definition of parallelogram, think of what's in the word parallelogram, parallel. So both pairs of opposite sides were parallel. Okay, that was definition. On a trapezoid, okay, the definition of a trapezoid is a quadrilateral, okay, with exactly one pair of, how should I say this? With, one pair of parallel sides. I'll just put the symbol there. With exactly one. Alright, so if both pairs are parallel, it's not a trapezoid. Okay, that means if only one pair of opposite sides were parallel to each other, then what's true about the other parallels, the other two sides? They're not parallel, that's right. Okay, so we got to draw something that has two parallel sides and the other two are not parallel. You got it? So watch this. Let's do it like, we'll do it about like that. Okay? Okay, I drew those so they're parallel, so those are my parallel sides, but watch, I have to draw my other two sides so they're not parallel to each other. So, like this. That pretty much looks like they're not parallel, doesn't it? Okay, and that thing right there, now watch. Right now I don't know it's a trapezoid because I haven't marked anything. Now it is a quadrilateral, but if I do this, if I put parallel and parallel, now what is this thing right here? Now it's a trapezoid because you have what? Exactly one pair of opposite sides parallel. These two right here, they're not marked, all right, so they're not parallel to each other. You get it? So you got a trapezoid is exactly one pair of parallel sides. All right, let's talk about some of these things. The two parallel sides we call the base of the trapezoid. So it's not just one base. There are two bases to the trapezoid. The non-parallel sides are called the legs of the trapezoid. Sounds very familiar, doesn't it? Remember we did this with triangles? But this is a trapezoid, okay? You got two bases and you got two legs. All right? Pretty easy. Yes, sir. Not necessarily. Doesn't have to be. For instance, I could, question was, are the legs the same length? Let's watch, I could do that. That's obviously not the same length as this, correct? Okay, so the two legs do not have to be the same length. I could even bring this in, oops, like that, couldn't I? That's still a trapezoid, right? Because these two, as long as these two legs right here are not parallel to each other and the two bases are parallel to each other, then it's a trapezoid. Has nothing to do with these two legs being equal to each other in length. And same thing with the bases. The lengths of the bases aren't necessarily equal to each other either, are they? Okay? Now, we do have a situation where you could have a trapezoid with equal legs, but we have a specific name for that. So let's do this. Let's see if I can draw one. Go like this. Now I'm just eyeballing this. Well, actually, you know what I could do? I could make sure it's exactly right by doing this. I'll just flip this around. Let's see, what are we doing? Transforming or reflect. There we go. Alright, so I didn't change the length of it. I put it right there, so let's scooch this in just a little bit more. There we go. Perfect. Piece of Jello? I guess it could be a piece of Jello. Now watch, what did I do? I copied and pasted, didn't I? Alright, and all I did was just flip it around, so I didn't change the length of it. So what's true about this length and this length? The two non-parallel sides, they're the legs, and they're equal to each other in length. That doesn't have to be true about every trapezoid. The first trapezoid that I drew, the two legs were not equal to each other. So you can have a trapezoid when the legs are not equal to each other. Alright? That's just a normal everyday trapezoid. But this one right here, the two legs are equal to each other. Now, think back. This is very familiar. Remember we talked about legs, we talked about bases, and that kind of refers back to triangles. Remember we talked about triangles having legs and bases and all that kind of stuff? Well, trapezoid, it's a lot of similarities to triangles, actually. They both start with T. How about that? All right, but that's not the only similarity. They have a lot of things. They have the word bases in common. They also have this in common. So what if I had a trapezoid when I had the two legs equal to each other? If I have two sides equal to each other, what do you think we call it? Isosceles, right? That's right. This is called an isosceles trapezoid. Okay, I'll just write it right there. All right, so isosceles means we got the two sides equal to each other. So it's an isosceles trapezoid. You know, we had symbols for stuff. We had symbol for a triangle. We had symbol for parallelograms and all that. We don't really have a symbol for trapezoid. I think when they refer to a trapezoid, they'll either use the whole word or they might just shorten it and just say TRAP, trap, okay? So there's no real symbol for a trapezoid. You would just write the word out or just shorten it to TRAP, all right? So we do have an isosceles trapezoid. So watch this. The first theorem, it says if a trapezoid is isosceles, then each pair of base angles is congruent. Now, remember, this is a base, right? And this is a base up here. Each pair of base angles are congruent. What are the base angles? Well, this one and this one. Those two angles, if this was an isosceles trapezoid, if these two sides are equal to each other, that means that these two angles are equal to each other. Again, very, very familiar. Do you remember that with isosceles isosceles triangle? Okay, watch. When I had the two sides equal to each other, what was true about the opposite angles? They were equal to each other. Remember that? Remember, this was called the base of an isosceles triangle. These were called the legs of an isosceles triangle. Very, very familiar, right? A lot of similarities between trapezoid and triangle. So if I said the two legs are equal, the two base angles are equal. Same thing on a trapezoid. Now, these two are equal. Does that mean that this angle up here is also equal to this angle right here?
Yeah.
It does? Look at that. That's an obtuse angle, and that's an acute angle. Is there any way? No.
I thought you meant the two top and the two top.
No, I pointed this one and this one. This top one and this bottom one. They're not equal to each other, but the two top ones are, right? These are, right? Because these two angles are formed from the same base. These two angles are formed from this same base. You get it? So it's from this leg to this base, the equal leg to the same base. Those angles are equal. Same thing up here. Now, what do you think might be true about this top angle? Let's just call this trapezoid ABCD. What do you think is true about angle A and D without even looking at a theorem? That's right, they're supplementary. Why? Because remember what's true about the two bases. They're what? They're parallel to each other. This would be considered a transversal, wouldn't it? And what are these two what are these two angles right here? Yeah, they're supplementary. What's the name of those two angles? What do we call them? Consecutive interior angles. That's right. So if I have two parallel lines cut by a transversal, the consecutive interior angles are equal. See how it's all coming together? All that stuff you learned way back about parallel lines and all that kind of thing, it's all coming back. All right, so if you learned it back then, it should make sense to you now. We good with that? Okay, good. Let's see. Okay, let's do this. Now, on parallelograms, what did we always put? We talked about the sides, we talked about the angles and all that. Then we talked about what? What did we stick inside there? The diagonals, that's right. So watch this. Look at that diagonal right there. And let's see if this works. I'm just going to try something. I want to flip it. Just reflect it. Let's see if that works. Now look, all I did was copy and paste it, okay? I didn't change the length of it. And if I did this, boom. What do you think is true about those two diagonals? They're equal to each other in length, aren't they? Okay? So, what can you say? Now, this is only true about an isosceles trapezoid. This is not true about just any old trapezoid, okay? We rarely talk about just a normal trapezoid. Most of the time when they give you problems in the book and stuff, I would say a lot of times, they'll talk mainly about an isosceles trapezoid because there's a lot more stuff that you know about an isosceles trapezoid than you do about just a normal everyday trapezoid, okay? So we're really going to concentrate probably more than anything on isosceles trapezoids. So the diagonals of an isosceles trapezoid are what? Are equal or congruent to each other. So what could I say here? I could say AC equals what? Yeah, DB or BD, okay? So that's true, again, about what kind of trapezoid? Just an isosceles trapezoid. All right? So there's a lot of stuff we know about this trapezoid. We know the base angles are equal. So these two down the bottom are equal. These two up at the top are equal. We know the consecutive interior angles are supplementary. So we know this and this add up to 180. Okay? Now, do we know anything about like bisecting? Does that look like it bisects that angle A? No, it doesn't. Okay, remember that only works with a rhombus. Okay, and this is definitely not a rhombus. Okay, so but you do know a lot of stuff about this. Does it look like the diagonals bisect each other on this trapezoid?
Yeah.
It does? They do intersect each other, obviously, right here, but nah, they don't look like they bisect each other. So we're not going to say that they bisect each other. Yep, because it's not a parallelogram.
Can you say that the triangle AD and the center point
P
and triangle BPC are equal to each other?
are congruent, you mean? Let's see. Well, you know this and this are equal, right? You know this side and this side are equal. I could almost guarantee they are. But what would the reason be?
But it doesn't split the top of A and B because
Bet you they are. I'm just trying to figure out. Why they would be.
They're like the same length.
I would say they are. I would just have to think a little bit longer, and I just don't want to take the time in class. But I would say they are congruent to each other. These two are definitely not congruent to each other. Would you agree with that? But these two have the same lengths right here. This is the same. I don't know. There might be some things you could do to prove a couple of the other angles equal to each other, but
If like both the intersecting lines are like the same length,
like this one and this one.
yeah.
Yeah.
That's like side.
Well, I'm trying to think of maybe, how we could say it is. I'm not sure how we could, but my guess is yes. That would be a guess. I can't say definitively, just because I'd have to do the proof on it and just see if it works out. And I just can't think off the top of my head right now. Maybe I'll try to figure out why they're congruent to each other. But that would be a good guess. It's a good observation. All right. All right. Let's go to another part of this. Let's see the next thing I want to cover. Okay. Here's another thing we're going to do with a trapezoid. This is just a normal everyday trapezoid. This is not necessarily an isosceles trapezoid. I can go longer now. YouTube let me go longer. I've gone up to 30 minutes and it hasn't, and it still goes on there, so sorry. Okay. Watch what we're going to do here. What's that? What is what? It just gets people to ask questions about why it's up there. No, I don't. Alright, we're doing this. So watch. Look what I did. I took this segment right here. This is one of the, what? Is it a base or a leg? It's the non-parallel side. It's the leg, right. Okay, so I took the midpoint of this leg, and then I'm going to come over here And it looks like the midpoint would be about right there. Took the midpoint of this leg. Now let's hope they connect like they're supposed to. Watch, and if I connect them, oh, look at that, perfect. So if I connected the midpoint of one leg to the midpoint of the other leg, that means this and this are equal, and this one and this one are equal. Remember, I didn't say anything about this being isosceles, okay? So I did not say this is an isosceles trapezoid. This works for anyone, any trapezoid at all. So what did I do? I connected the midpoints of the two legs of the trapezoid, and I got this line segment right there, okay? It connects the midpoints, right? So they call this thing the mid segment. How about that? It's not rocket science, is it? All right, they call it the mid segment. It looks like they make it one word. It looks like I split it right here. Okay, I wasn't sure, but it looks like in the book they make it one word. Okay, it's mid segment. And we have a theorem for the mid segment. They say, okay, well, big deal. Who cares if that's the mid segment? This is actually kind of interesting. I would have never probably thought of this on my own unless I was taught this somewhere. Watch this. I tell you what, since I got this little program here, let's see if I can do. I've never tried this before. Watch. If I took A, I'm going to copy it and paste it, and I'm going to put it down right here. Okay. Let's scooch this over. Hopefully I have enough room. I might not. We'll see. And I take this and I put it. Oh, I'm not going to have enough room. Tell you what I'm going to do, just for the sake of this. Group that together. Watch, I'm just gonna. There we go. Yeah, you got to say that. Alright, now watch. Let's see if it works now. So let's take this segment. I'm going to copy and paste it. Put it right here. Hopefully I got enough room now. Copy and paste that. Yep. Now watch what I'm going to do. I'm going to put it right there. Alright? So that's that right there. Now watch this mid segment. If I copy and paste this, and I put it right there, how much of A, B, and D, C do you think that mid segment is? It's exactly half of it. Exactly right. And that's kind of cool because I was never able to do that on the board, you know. So it's kind of cool that I got this program now that can do that. Because watch, if I did this, if I just copied and pasted that, and I put it right on the end, yeah, it's pretty close. Not exactly, but you get the idea. Okay, you can see that two of these makes one of these. Would you agree? So let's get rid of that. That's kind of cool. Just thought of that off the top of my head. How about that? All right. So watch. What could we say here? We could say that AB plus DC, right, is actually, let's do this. If I add them up and do what? Does that equal EF? Okay, right. 1/2 of this. Okay, if I add the two up, okay, add the two bases together. If I take the sum of the two bases and then take half of it, it's going to equal what this mid segment is. You see that? Or I could write it another way. I could have said what? If I double EF, that's going to equal AB plus DC. Isn't that the same thing? Right? Just multiply both sides by 2. So if I take this EF and double it, it's going to equal the sum of the top and the bottom, the two bases. And you can see what they're going to do there. They're going to put some numbers in here, right? I don't know. Let's just make something up. Let's say this is 6. Let's say this is 10. And I asked you to find what this mid segment was, EF. What would you do? Take 6 plus 10 is 16. And then what do? Is that 16? You take half of that. So what's the mid segment? It would be 8. Make sense? It's kind of like the average, right, of the top and the bottom. It's kind of like the average of the bases. Right? You add the two numbers together, divide it by 2, and you got the middle one. You okay with that? What if I did this? What if I didn't tell you? Now you know what that's going to be. You know it's going to be 10, but I'm just doing this to make this easy. How would you find DC? Yeah, that's right. Instead of taking these two, adding them and taking half, what are we going to do? We're going to go the opposite. We're going to double this, and instead of adding, what do? Take away. That's right. So you double this, which is 16, you take away this one, which is 6, so 16 minus 6 is 10, right? So if I give you the middle one, you should be able to find either the top or the bottom. Now you got to know at least one of the top or the bottom, don't you? You can't not know either one of them. But if one's missing, you should be able to find them all. You okay with that? All right. Okay, we're running a little later than I wanted to. We got one more thing. We got to talk about kites now, don't we? All right. Let's try to draw one here. You like kites?
I went to Ocean City. I saw chickens walking the boardwalk and this kite came down straight in the face.
I was watching Funniest Home Videos, and there's one of that cracked me up. It's funny when other people get hurt, isn't it? What do I go? Reflect. Thank you.
You can fly on a kite?
Say what?
Like if you get a big enough kite?
Can somebody can it pick you up? You mean?
Yeah, like if you hold on to
Oh yeah, hang gliding. That's basically a kite, and sure, if it's big enough, absolutely. Yeah, we should make it.
it should be around the
Yeah, I'm not gonna be on that.
Nah.
Yeah.
Okay, then.
What's the channel number?
Not that one.
Okay.
Put some rocks in. Don't fly too far.
Guess I should have done this before
Yeah, man.
before you started. Oh, what did I do? I didn't even copy it. Daggone it. So stupid.
Yeah, dude.
All right, let's try this. Here we go. We got a kite. An hour later, we got a kite. Okay.
It's like a UFO.
It's probably what most UFOs are. They're probably just people's crazy kites. Yeah. All right, there we go. We got a kite, I guess. All right, here's the first thing. A kite says a kite is a quadrilateral with exactly two pair of consecutive congruent sides. What in the world does all that mean? Look, consecutive congruent sides, so a pair. This one and this one would be equal to each other in length. In fact, when I drew this thing, I copied and pasted and put it right here, okay? Then I took this one and I copied this and pasted it here, so this one and this one are equal to each other. So again, it says it's quadrilateral with exactly, not just one, but exactly two pairs of consecutive congruent sides, all right? Now, they are not parallel to each other. This and this are not parallel. This and this are not parallel to each other. Couple theorems real quick and we'll be finished. It says if a quadrilateral is a kite, then its diagonals are perpendicular. So let's draw the diagonals. Now hopefully I drew this accurate enough. Looks like it's a little bit off, but you should get, that's pretty good actually. Alright, so there's the diagonals of a kite. Guess what they are? Forms a nice right angle right there, so the diagonals are perpendicular. So you might want to write that down. I just don't have time to write all that down. But the diagonals of a kite are perpendicular. So if I drew the diagonals from corner to corner, it's going to form a right angle. What else? What other figure did we talk about recently where the diagonals are perpendicular? Do you remember? A rhombus. That's right, a rhombus. All right, so the same thing is true about a kite, even though it's not a parallelogram. All right, and it says if a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. It says exactly one pair are congruent, which means it would be the one in between the two. Well, let's see. How would I say this? Well, it says exactly one are congruent. So which one? Is it this one and this one, or this one and this one? I guess it depends. I think it's this one and this one. Is that the one you're talking about? Yeah. It's probably that one and that one right there. Okay? So it's the one between the two unequal sides. Let's say that. Okay, it doesn't say it in here, but it looks like that's... Well, yeah. It looks like that's the one, okay? It's the one between the two unequal sides. You get it? So you got side, angle, side kind of a deal. You see it? Side, angle, side. So it looks like this triangle right here is what to this triangle down here? It's congruent to each other. Exactly right. Okay? So there you go. So that's what we know about a kite. It's a weird looking K. But, all right, so what do we know? We know basically two things. The diagonals do what? Perpendicular. And it has exactly one pair. That means that this angle right here is not equal to this angle right here. So I'll put 3 arcs. Does that make sense? Don't get confused. So it says there's exactly one congruent pair of opposite angles. Right? So that means these two are not congruent to each other. These two are. We good? All right. So let's give you some work to do. Now this is the only way you learn how to do this stuff, by doing problems. So we're going pages 440, 441, 8 to 11. There's like 3 different sections I broke it down into. This is 16 to 27. Make sure you write them down. 41 to 44. Look at that. Perfect timing. Okay, there it is.